Next topic is power handling capabilities of HVDC line. This is a sending end side. This is receiving end side. Sending end side having rectifier station. Receiving end side having inverter station. This is converter 1, converter 2. Normally, converter 1 or converter 2 both are same depend upon firing angle that will act as a rectifier or inverter. The firing angle alpha less than 90 degrees act as a rectifier station. The firing angle alpha greater than 90 act as a inverter station. So depend upon firing angle that will act as a rectifiers or inverters. This is HVDC line. The current flowing in HVDC is ID, that is equal to VDC1 minus VDC2 by R. VDC1 is a rectifier station voltage. VDC2 is inverter station voltage. The DC power PDC in controlled by adjusting the voltage between rectifier voltage VDC1 and inverter voltage VDC2 to get desired DC current. IDC is equal to VDC1 minus VDC2 by R. The current flowing in DC line IDC is equal to VDC1 minus VDC2 by R. Take this is the equation 1 where R is the resistance of DC circuit, VDC1 is a rectifier voltage, VDC2 is inverter voltage. The DC power output PDC is equal to VDC into IDC. Substitute IDC values in IDC. So where VDC is equal to the VDC having the rectifier voltage VDC1 plus inverter voltage VDC2 by 2. From equation 1, VDC1 minus VDC2 is equal to IDC into R. Rearrange this equation. VDC1 minus VDC2 is equal to IDC into R. Here two ways we can control the power flow. One is by using tap changer control and other is phase angle control. In these two ways, phase angle control is faster than the tap changer control. From equation 3, VDC1 minus VDC2 is equal to IDC into R. From this equation, VDC1 is equal to VDC2 plus IDC into R. This is equation 4. In this equation 4, VDC2 is controlled by the inverter terminal and IDC is controlled by the rectifier terminal. The DC power at rectifier end is PDC1 is equal to VDC1 into IDC. This is equation 5 where PDC1 is the rectifier DC power, VDC1 is the rectifier DC voltage. IDC is equal to IDC1 is equal to IDC2 because the current is same in entire DC transmission. Current in IDC is equal to IDC1 is equal to IDC2. The current is same. Substituting equation 1 in equation 5, PDC1 is equal to VDC1 into VDC1 minus VDC2 by R. So overall the rectifier power PDC1 is equal to VDC1 square by R minus VDC1 into VDC2 by R. This is a rectifier power. The DC power at inverter end is PDC2 is equal to VDC2 into IDC. where PDC2 is the inverted DC power, VDC2 is the inverter DC voltage. So already we know all the currents are same. So substitute equation 1 in equation 7. PDC2 is equal to VDC2 into VDC1 minus VDC2 by R. So PDC2 is equal to minus VDC2 square by R plus VDC1 VDC2 by R. Here the negative sign indicates that power is received by the inverter end. The power loss formula, PL is equal to PDC1 minus PDC2. PL is equal to VDC1 into IDC minus VDC2 into IDC. So rearrange this equation, VDC1 minus VDC2 into IDC. We know the IDC value, VDC1 minus VDC2 by R. So overall the power loss is equal to VDC1 minus VDC2 whole square by R. This is a power loss formula. From equation 9, by increasing the difference between VDC1 and VDC2, then the DC power flow is increased and then DC power loss also increases. Power in the middle of the DC line, that is equal to PDC1 PDC2 by 2. So overall we get the power in PDC1 minus PDC2 by 2. So power in the middle line is equal to VDC1 square minus VDC2 square by 2R we get. Power at sending end side is equal to power in middle plus half of total losses. Substitute the values of power in middle and total losses. We get VDC1 minus VDC1 square minus VDC2 square by 2R plus VDC1 into VDC2 whole square by 2R. Power at receiving end side is equal to power in middle minus half of total losses. We get this formula, power at receiving end side. And generally equation of DC power flow is equal to VDC1 square minus VDC2 square by 2R plus R minus VDC1 minus VDC2 square by 2R. So this is plus for positive sign indicates the sending end power, negative sign indicates the receiving end power. Choice of converter configuration, that is static converter configurations. For a given pulse number, select the configuration such a way that both the valve and transformer utilization are minimized. In general, converter configuration can be selected by the basic commutation group and the number of such groups connected in series and parallel. Commutation group means set of valves in which only one valve conducts at a time. Let Q be the number of valves in a commutation group, R be the number of parallel connection, S be the number of series connection. Then the total number of valves will be QRS. Q is the valve in commutation group, R is the number of parallel connection, S is the number of series connection. Pulse number P is equal to QRS. So this is a diagram, converter configuration. First row first column, first row second column, first row R. This is a DC voltage. Converter configuration decides how many valves we using, how many valves required. Valve voltage rating is nothing but valve voltage rating is specified in terms of peak inverse voltage it can withstand. The valve utilization is the ratio of peak inverse voltage to average DC voltage. Converter average DC voltage is Vd naught is equal to SQ Vm by pi sin pi by Q. Vd naught is equal to S into Q by 2 pi integral minus pi by Q to pi by Q Vm cos omega t d of omega t. That we guessed SQ by 2 pi Vm sin omega t minus pi by Q to pi by Q. Overall we get SQ by 2 pi Vm 2 sin pi by Q. peak inverse voltage. If Q is even, then the maximum inverse voltage occurs when the walls with a phase displacement of pi radian in conducting, and this is given by peak inverse voltage is equal to 2 Vm. If Q is odd, the maximum inverse voltage occurs when the wall with phase shift of pi plus pi by Q in conducting, and this is given by 2 Vm cos pi by 2Q. Utilization factor is the peak inverse voltage by Vd naught. Substitute the value. If the Q is even, 2 pi by Sq sin pi by Q. If Q is odd, pi by Sq sin pi by 2Q.